Okay, so today is pretty much a review of things we've already done, just a little bit of a different application. So we're going to talk about the idea of the integral being an accumulator again, and then we're going to revisit rectilinear motion. For those of you who don't remember, rectilinear motion was the problems where you've got things sliding along one axis. Okay, and then I showed you how to do those schematics. We're just going to talk a little bit about that, and then we'll be done. So, yeah, solve problems, practice problems, rectilinear. Calm down, relax at some point today. Yeah, good luck with that. Okay, so here's the picture. And we've done this a lot. We talked about this when I introduced the fundamental theorem of calculus part 1, where t's become x's and stuff like that. But the bottom line is I have a picture of the function f. I'm defining g as the integral of that function. Okay? Which means g is defined as the area under the curve. Now, before we get to answering the questions, let me ask you a couple questions. And this is something I would recommend doing every time you look at a problem like this. What is g prime? Good. What's g double prime? F prime. Okay. And again, you see why this is a review. Okay, so first things first. What's g of 0? Lauren? What's g of 0? Why? Perfect. Good. Liam, what's g of 1?
G of 1 is... Wait, no,
You're overthinking this.
for sure. Oh, wait, G of 1 would be 1. Right? They line up? Yeah. Yeah.
What is it?
1.
Why?
Because of the area from the 1 from 0 to 1.
Yeah, it's the area of the curve. It's the area of that little triangle.
Right.
Okay, good. What's g of 2? Kush? G of 1. Oh, did you not hear me? Oh, because you guys have been chattering the whole time I've been trying to do my gate today. And it's that close to forcing me to act like a kindergarten teacher and separating you, giving you timeouts. I asked what g of 2 was.
G of 2 would be 3.
Pretty close to it. This group. Maeve, what's g of 4? This one I'll have to be approximate.
A little over 4.
1, 2, 3, 4,
A little over
5, maybe a little over 6.
Yeah, a little over 6.
Okay. What happens when we go past 4?
Just goes
Right?
it goes down.
Don't use pronouns. What's it?
The area.
Good. So, what's bigger, g of 4 or g of 6? Okay, good. What's bigger, g of 3 or g of 5?
3. Wait, no, they're the same.
Well, you don't know why.
Because if you kind of look at it, both of them have the same amount, and because one of them is negative, the other one is positive, it cancels it out.
Perfect. Okay, good. Now the fun part. On your notes, sketch a graph of what you think G looks like. Okay, so this was 0. This was 1. This is 3. Maeve, what did you say 4 was? About
6.
6. And then G of
That was 6.
what?
That was G of 6, wasn't it?
No.
Oh, no, that was 4.
G of 4.
Sorry.
And then we didn't answer this question, so we'll just leave that blank for a second. Okay. What does G look like? And full disclosure, I hate these kinds of problems. They're very reminiscent. I remember when I had physics that long ago, when you have to do the graphs of like velocity and position and acceleration. I hated them. You know, here's a graph of Billy riding to school. Describe what happened. You know what I'm talking about, right? Does everybody else hate them?
Yeah.
Okay, good. So we're on the same page there. These types of problems are reminiscent of that.
It's going down.
They always get there, there's never any true reaction.
No. I'll design a problem where Billy gets hit by a bus.
Oh, wait,
Okay, thank you.
Okay, then he has to crawl to his cell phone. So Billy's riding to school, he's hit by a bus, now he crawls back to his cell phone.
You know what, I actually appreciate it more before you
It would be more interesting, wouldn't it?
Will he make it there before school starts? If he leaves his
that's-
house at 8,
it's a great
and
question.
he gets hit at 8:10.
Great
He
question.
left early because he thought he felt something.
Okay, so before we do this, let's talk about where does G have a maximum? Why?
It's because it's accumulated all the positive area that it will ever will.
Good. Where does G have a minimum?
0.
Why?
Because it's accumulated no area.
What about 6?
Well,
There's negative area in 6.
there's negative area, but there's already all the positive area.
So you're saying that even though this has negative area, this is going to be smaller than that?
Yeah.
Explain.
Because it's already accumulated more positive than negative area by the time it's 6.
Everybody good with that concept? Yeah. Okay. This area, which is positive, is bigger than this area, so therefore G of 6 is going to be a positive value. We don't know exactly what it is, but we know it's positive. So therefore the minimum is at 0. Could you do a first derivative number line for G? We did this a while ago. If you'll recall, the first derivative number line, you need to know where G prime equals 0. Okay, so where does G prime equal 0? Nothing over here, so we're actually going to do a G prime ray, if you will, or a G prime number line. Does G prime hit 0 anywhere else? Are you sure?
No. No.
Wait, yeah, sure.
How is G prime defined?
Oh, it's just,
It's F. So where are the other zeros? 4. Good. Okay, that's an important point. Does everybody follow why that's there? We define G prime as being f of x. Where is f of x equal to 0? It's equal to 0 here, and it's equal to 0 here. Then we test regions. Okay, and actually we'll clean this up. We'll put a 6 here. We'll get rid of this stuff. Is G prime positive or negative between 0 and 4? Positive. Why?
it's above the,
Yeah, it's above the x-axis. What about between 4 and 6? Negative. Okay, and we get that. And what does that tell us now about 4? It's a max. But we knew that already because Lauren explained to us why 4 must be a max. You could then go on to do a G double prime graph, talk about concavity as it applies to G, where we'd have to look at the f prime values of the function. Now, when we did these, we realized that the graph of the G prime function, sorry, I said that wrong. Yes, the graph of the function looked similar to the shape of the first derivative number line. Having done this, what does G look like?
It's like a parabola
Okay. Where would it hit its max?
at 4.
So just for giggles, I'm going to put it up. I'm going to change colors first of all. I'm going to put it up here. Any other crucial points that I need to know about?
It starts at 0,
It does start at 0.
and then after it hits its max at 4, it goes down.
To where? I agree. I like 3 points. I got a starting point, which I agree with. I got that max. I'm not really sure how high it is, but we'll go with that. Where am I going to put a point at 6?
Well, you would have to find the area.
Guesstimate.
I'd
Up
say
here?
6. No, lower.
Here, down here,
Like, maybe like in between 1 and 2, I guess.
like here.
Yeah.
What were you going to say?
I was gonna say 3.
Up at 3?
Well,
Here?
like not the same, but like if G of 4 equals 3, then that's like the same. Think about
It's fine. And it's an approximation. What wouldn't work is if we had it down here, because based on what Lauren told us before, we know that G of 6 must be a positive value. And there's never any point on this graph where the negative area is bigger than the positive area. So that entire graph of G has to be above the x-axis. Okay, and maybe it looks like a prettier parabola. Maybe it could be a lot of things, but who cares? We just want a general shape of what that graph is. Okay. Questions on this? This starting step here is going to help you tremendously when you start to answer all these kinds of questions involving this particular scenario. And this pops up a lot. Here's a function defined as the integral of another function. Okay, and understanding what each of those components mean. Okay. This is the area under the curve. G is represented by the area under this function that we're looking at. G prime of x represents the actual values of the function. G double prime is the slope of the tangent lines to that function. Okay, so Jen, just for giggles, what is G double prime of 3.5?
positive something.
No, it's actually negative.
Of what?
It looks like it would be like, I'd go with -1. Yeah, something like -1. In other words, what is the slope of that tangent line at 3.5? Okay. What would G double prime of 4 be? So what would it be? Undefined, correct. Very good. Okay. Same is true about G double prime of 1 would be undefined because we have a corner. Okay, let's move on. This is more of the same stuff. I'm not going to go through all this again because it's just more of an example. You seem to have a pretty firm grasp on it here. The only difference here is I simplified it into triangles and a semicircle, but it's the same idea. We also already did the number lines and the relative maxes and mins. Excuse me. When you're dealing with a problem like that, like this, I should say, be aware of what's happening as you're moving from left to right. So notice at -6, I have a value of 0 if we're talking about the area under the curve. As I move to the right, we continue to add negative area, but then all of a sudden I start to add positive area. And you'll notice I'm using the phrase adding negative area. I'm not subtracting area. I'm adding more onto it. It's just the value I add on happens to be negative. Okay. And then I included this in here just because you might want it as a reference. There's nothing in here that you don't already know. Like, for instance, when the velocity is 0, the particle's not moving. When the velocity is 0, it could be a turning point, but doesn't have to be. Remember, particles can stop and then keep going in the same direction. Okay? Billy's riding to school, he drops his phone, he stops, picks up his phone, and keeps going. He doesn't turn around and go home. We're not even going to mention what happens when he gets hit by the bus. It was a bus, right?
Yeah.
Okay. And again, more of the same stuff. We've talked about this quite a bit. The derivative of the velocity, derivative of the position is a velocity, derivative of the velocity is acceleration, so it ties together into that one big statement that relates acceleration, velocity, and position. And I'm thinking you probably did a ton of this in physics. Is that true? Okay, good. So I don't want to beat a dead horse here. This is the other one that is important, the difference between total distance and displacement. Okay. Remember, total distance, you're going to turn all those negative distances into positive. That's why you want the absolute value. Okay, I move forward 3 feet, positive 3. I back up 3 feet, negative 3. My displacement is 0 because I added positive and negative. My total distance is 6 because I took the negative distance and made it positive. Common mistake is people forget where to put the absolute value. It goes with total distance for that reason. Okay. This has started popping up here, and that is, don't forget to add initial conditions to a scenario. This happens to be a particle on a number line. However, we've seen examples of this where, didn't we just do an AP question where you're filling a tank or something and there's or is it car? I forget what the one was. But there was something where you had to add 250 to the start. You know, if you're looking at a function that measures the amount of cars in a parking garage at a certain time, you have to realize how many cars you started with and add that to the starting case of your function. Where this relates to is not assuming that the particle starts at 0, you may have to add or subtract wherever it starts on the number line. Okay? Oh, is that what that is? Okay, beautiful. And then more, we've done this already, so it's there if you want to take a look at it. But it's just, again, taking the velocity, finding out where it's equal to 0. That would be possible turning points. So again, you have to check regions. So I did that, and I realized that both of those, 2 and 7, are turning points. So the particle moves to the right, hits 2 and turns around and comes back. And then after 7 seconds, it turns around and goes the other way. Blah, 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 total distance, great. And I think we're just about done as I fly through this, because I want to get to the quiz. Okay, good. This would have been obviously a much longer lesson if we hadn't already covered rectilinear motion, but we did it quite a bit when we were talking about derivatives.
Is this a no calculator or calculator?
I believe it's a no calculator, but I will have your answer.